reversing the arrow and hence reversing the sign here, so it becomes plus 234, then plus our minus 966. So this is the route that we are taking to get to the product. That should be equal to this. Okay, so this gives us negative 732 kilojoules per mole. So basically this is how you use your Hess cycle given formation enthalpies. You have to create it and construct it in this manner. Okay, let's go on to our next example. If you're given combustion data, which is the next possibility, so you have to check your question. Did it give you formation data? Did it give you combustion data? So when you're given combustion data, then your Hess cycle is going to look like this. You have your reactants here to your products. So this is the enthalpy change of reaction that you're interested in. It can also be the enthalpy change of formation, because your reactants can be actual elements that are used to form a specific product. So reactants slash elements here to give product. So for this question, you may be asked calculate the enthalpy change of formation of, or it can be asked, phrased as calculate the enthalpy change of reaction for the following reaction. The important thing is that your reactants or elements can burn to give combustion products, and your products can also burn to produce combustion products. So this is how we link. So we have to have an arrow pointing down and arrow pointing down. This becomes our enthalpy change of combustion for the reactants, and this becomes the enthalpy change of combustion for the products. So what it means is that my reactants should be able to burn and my products should be able to burn to give specific products. So this is how we link it, and our products are usually carbon dioxide and water. Okay, so let's think about let's go to a specific example. Okay, so calculate the enthalpy change of formation of pentane. So by formation, and I'm going to calculate the enthalpy change for the following reaction. And so the enthalpy change of formation. So we should have constituent elements for pentane there. Carbon plus hydrogen plus oxygen. Here we are forming our pentane plus oxygen here. Okay, so that's the reaction. So this side, what burns to produce carbon dioxide and water? Our carbon and hydrogen can burn to produce carbon dioxide and water. That side, our pentane can also burn to produce carbon dioxide and water. Oxygen does not burn. Okay, so we are burning here 5 moles of carbon. So the enthalpy change for the combustion of carbon is negative 394. So we're going to have to say 5 times negative 394 to get a total of 1970 here. And then we have 6 moles of hydrogen. So we now have to say 6 times negative 286, and we get a total of 1716. So we have to add these 2 enthalpy changes to get a total of negative 3686 here. Now this side, our pentane can burn to produce carbon dioxide and water, and we have 1 more here. So 1 more here is negative 3509. So that's the total energy change there. So we now need to think as before that for us to get to this product, we can go via this route, this side here, and then this side. So we have to reverse this arrow here. So and when we add these two, this should be equal to this energy change, which is in this case our enthalpy change of formation of pentane. So those are routes A and B. So we have to reverse B, so negative B. So our enthalpy change of formation becomes negative 3686, which is this. So no need to reverse the sign here because our arrows are pointing in the same direction. But here, our arrows are in opposite direction, so we have to change this sign to a plus. So plus 3509. And then our enthalpy change, the overall energy change that we're looking for, becomes negative 177 kilojoules per mole. So basically this is what you do. This is how you manipulate Hess cycle diagrams. Okay, We talked about mean bond enthalpy before. So you can also calculate enthalpy change from mean bond enthalpies using Hess cycle. It's all about remembering that when you're going against the arrow, you change the sign of the enthalpy change. So here's another example, the last one in this video. We need to calculate our enthalpy change for combustion for this reaction here. This is methane burning to produce carbon dioxide and water, and we are given what? Mean bond enthalpies. So if you're given mean bond enthalpies, then in this case we see that we have our methane here, which can these are constituent elements that can be used to form our methane, and our water. These are also constituent elements here. So this idea, what we need to do is, we have how many bonds, carbon to hydrogen bonds here? We have four times our carbon to hydrogen bonds here. So to break this into these constituent elements, we should take in 1652. So to break methane to its constituent elements, we will require this much. And then for oxygen, to break oxygen into oxygen atoms here, we have to break 2 moles of these oxygen to double oxygen to oxygen bond. So 2 times our 498, and that's 1900, that's 996 in this case. Okay, so this is what we are doing. So the total energy that's needed to break these bonds is going to be plus 2648. How about if you wanted to break these bonds here? You have okay, let's begin with this one. For carbon, you have 2 of those in carbon dioxide, carbon to oxygen double bond. So 2 times 805, here it is 805. So that's 1610. So 1 more here. But you have 2 moles of water. So let's add that. How many oxygen to hydrogen bonds you have in 1 mole of water? You have 2 of those, but you have 2 moles. So 2 times 2, 4. 4 times 4, 64. That's 1856. So here our reasoning is, we are breaking these bonds, these compounds into their constituent elements. Breaking these compounds into their constituent elements. This is how we linked this. This is similar to the structure of this is similar to the Hess cycle we saw for what? For combustion enthalpies. Okay, so let me just go back to it. See the structure here. The arrows are pointing down from here to here. Only that here we have combustion products, but in this case we have constituent elements. So we are breaking this not by combustion, but we are thinking we have to break these bonds into the constituent elements. That's the reasoning. So these tend to have a similar structure. So that being said, we have a total here of 30,466 and a total here of 2,648. But for us to get to calculate our enthalpy change here, the question is what? We are calculating the enthalpy change for this reaction here, which would be combustion. Enthalpy change of combustion of methane. So we can get to these products via route A and route B, but we have to say negative B. We have to put an arrow that's going in the opposite direction for B. So we have to change the sign there. So it becomes what? Plus 2,648 here minus this, we have changed our sign there. It was a plus, it becomes a minus, minus 3466, and we have our negative 818 kilojoules per mole. So these are the basic structures that you are going to find for your Hess cycle diagrams. So I'm going to give you more examples so you practice utilizing these Hess cycle diagrams and the Hess law. So we'll continue with Born-Haber cycles in the next video, where you're going to see the Hess law at play as well. So enjoy your studies. See you in the next video.